Good evening. I welcome you all for the week 10 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Now let's get on to the session. As usual, we'll go through a brief recap of the lectures of week 10. Week 10 had 8 lectures and they were based on polymer processing and recycling techniques. So lecture 70 was on polymer processing. Uh, It was on uses. Their shaping operations such as extrusion, dies, stretching, rolling, blowing were discussed. And then the blow molding operation was explained in detail with each steps. And then the time scale for polymer processing operation, like the cycle time for each of the polymer processing operation and the production rate. For example, a film blowing production rate is 100 to 1000 kg per hour, which is really mind boggling. And then a coating calendering operation takes 1 to 2 meter per second. Uh, and then the mixing and polymeric operation was discussed, where the mechanism of mixing, the laminar mixing and the dispersive mixing were discussed, where the dispersive mixing is used for dispersion of fillers filler agglomerates and breakup of blend domains. Happens in case of the dispersive mixing. And certain equipments which are used for mixing operations like open mixers, and then internal mixers like Banbury and Sigma mixers, and continuous mixers like single and twin screw extruders were discussed in the lecture. And then lecture 71 was on flow simulations. So in this, the modeling of polymer processing, which is actually a multi-scale phenomena, was discussed. Here the continuum description uh, uh, was discussed, where the system of engineering interest of materials, the macroscopic behavior, the single phase polymer and multi-phase mixtures, uh, these concepts were discussed. And where in the continuum description, there is an assumption that the material is made up of material particles and they are distributed everywhere, and between two material particles there are infinite number of material particles. This is basically the continuum description. And then the molecular description, which is based on the statistical mechanics, was discussed, which is this is for while the molecular description is for extremely small systems where hundreds and thousands of molecules are involved. And ultimately the microscopic behavior, which describes the properties of the material, is estimated using this molecular description. And then what are the transport phenomena processes involved in polymer processing? Like it involves mass balance, momentum balance, energy balance, species balance, and then evolution of volume, fraction, orientation. These equations are all solved based on the continuum description. There is also molecular dynamics and coarse-grained dynamics, which is based on the momentum balance. Which is nothing but the second law of motion is solved for the molecular dynamics. And then the equation for conservation of linear momentum and conservation of energy, and what are the available different softwares available for polymer simulations, like computational fluid dynamics based, which is a finite volume method based, and finite element simulations. These are all generic R&D packages which can be used for any system, whereas there are also processing simulators like mold flow, film blowing simulators, resin transfer molding simulators, etc. And what are the models that can be used to describe? Like there was discussion on the generalized Newtonian models, like power law model, Hershey-Buckley model, and then viscoelastic model like Oldroyd, Finney, and PGT model were all discussed in this lecture. The next lecture was on processing for recycling, where sustainability was the main aspect of this lecture. So Here, the recycling methods, the primary recycling methods, and then the secondary recycling was discussed. Where in secondary recycling you have downcycling as well as upcycling, and then recovery and conversion, where you can recover the monomers. Or it can be converted to some oil and char, which can be used for some some applications. And then also conversion to energy. These were all discussed. And then what are the operations that are to be performed on a polymer before recycling the polymer. So like separation and sorting, so there can be macro separations like sieving, optical sorting, or density difference based sorting, or magnetic sorting, or eddy current based separations. Or there can be micro separations or molecular level separations. So like molecular level separations can be based on use of solvent and anti solvents. And then consolidation, cleaning, cutting, crushing, granulating, and grinding operations, machining required for polymeric material. So these were all discussed in operation before recycling. And also what are the pre-processing and processing conditions which are based on like temperature. For example, uh, uh, wide range of processing temperatures are applicable for the case of polymers. For example, LDPE, the temperature is 260, whereas PVC it is 180 to 210. For PET it is 280 to 320 degrees. So these aspects were discussed. And then what happens to properties during multiple recycling. For example, there was a discussion on decrease in molecular weight of PET and decrease in impact strength of PET, which can be due to contaminations like acids producing contaminants like polyvinyl acetate or polyvinyl chloride. And then how does there's a color change in case of HIPS, high impact polystyrene. The color changes from white to yellow, and similarly, there's a drop in impact strength as well. And how what happens to the modulus in case of a polycarbonate was discussed. And then what are the effects of water or other contaminants like dyes or pesticides. And their impact, especially the impacts, since the recycling operation involves very high temperature, the impact of these contaminants which leads to the chain scission or any other side reactions could be very high. So these aspects were discussed in the polymer processing for recycling lecture. The next lecture was on recycle up down cycling. This was again on sustainability. So how waste is handled in India, what are the challenges in waste handling process was discussed. And then additional challenges during a mechanical recycling process, because it involves a lot of complex transport phenomena like multi-phase systems, the rheological behavior and the heat and mass transfer involved in these. And nuances in each of the processing techniques involved were discussed. And what are the upcycling processes like mechanical upcycling, chemical upcycling, and designed for recycled polymeric materials. So instead of trying to match the properties of a virgin polymeric material, how can we design materials with specific properties based on the recycled polymeric materials itself? How can we set standards for these kind of recycled polymeric materials instead of trying to match the uh, you know uh, the uh, a virgin polymer. So this was discussed. And then how do you upcycle uh, polypropylene and LDPE through blending. So these aspects were all discussed in the recycle up down cycling lecture. The next lecture was again continuation of recycle up down cycling. Here again, the concepts of biocomposites, like making composites out of recycled polymer and then natural fibers. How can these composites can be processed effectively for specific applications. And what are different equipments that can be used, like twin screw extruder was discussed. And then polymerization and molding techniques like reaction, injection molding, and then resin transfer molding was discussed, in which a biocomposite sandwich structure was discussed through resin transfer molding. The next lecture was on flow behavior. So here the introduction to rheology, the concepts of rheology was brought into picture. So what is a polymeric fluid flow? So what are the polymeric fluid flow as a product? So for example, as products, the fluid flow is involved in when in like in case of foods like your sauces or ketchup or jams. For example, a sauce should come out of the bottle easily, whereas once it comes out, it should stay, it should maintain its shape on the plate. And also how can it be easily spread on a bread, and the jam should be solid like, and when you use a spoon it should spread easily. So these are fluid flow involved in polymeric fluids as products. And then how do you optimize a formulation to have these specific fluid flows, uh, and what are the effective performance was discussed. And then a polymeric fluid flow in processing, like you can have polymeric solutions or melts, pre-polymers, resins, and how the the fluid flow in plays a important important part, especially in getting a optimum microstructure and having a efficient processing method with less cost and energy involved. And then what are the concepts involved in molecules in flow, like classifications based on flow behavior, like you can have polymeric solutions, and these solutions can be dilute, semi dilute, or concentrated solutions. And then polymer melts, where you have a entangled set of macromolecules, and then cross-linked polymers can be there. So there can be either a physical cross-linking or a chemical cross-linking. And then mechanisms that affect the flow of macromolecular systems. So your molecular flexibility, like your rotation or vibration around the backbone, bending, stretching, torsion, and then molecular interactions like your repulsion, or your van der Waals interaction, inter and intermolecular intramolecular interactions, and you can have a hydrophobic and hydrogen bondings. So these all affects the flow of macromolecular system. And then entanglement and molecular architecture, like a linear or branched or cross-linked system. So if a polymer is linear or branched or cross-linked, the flow behavior will vary. So these aspects all affect the flow of macromolecular systems. And then the interaction with solvent, like your Brownian motion and your drag and friction and hydrodynamic interactions. So these were all discussed. And based on the flow scenario, what kind of response is to be considered in case of steady flow or unsteady flow, when presence of fillers are there, and when polymer is pushed through a porous media. So depending on the scenario, the flow behavior and the response of the macromolecules vary. So these aspects were all discussed in the lecture on rheology. The next lecture was on cross-linking. So what are the cross-linkers used for different polymeric systems? Like what happens in the case of a step growth polymerization? For example, in case of Risol, a thermal cross-linking by dehydration, it leads to cross-linking process. Whereas in Novalac or epoxies, amines are used as cross-linking agents. And then in case of chain growth polymerization for polydienes, butyl lithium is used for polybutadiene, and for polyethylene, chemical or thermal or radiation based cross linking can be used. And then the extent of reaction for step growth polymerization. Extent of reaction for cross linking for a step growth polymerization was discussed. And then cross linking in rubber, the cure time, and how in industry, using oscillatory disc rheometer or using a moving disc rheometer, the flow behavior is analyzed. uh, And then cross-linking and gelation, the viscoelasticity, the concept of viscoelasticity of cross-linking and gelation, that is the change in dynamic properties. So how the modulus, the storage and loss modulus vary over time upon gelation. And initially, when it is in a sol or monomeric state, your your viscous behavior dominates, whereas as cross-linking happens, and the polymerization or cross-linking happens and the gelation happens, your solid like behavior or storage modulus starts increasing, and there is a particular point at which this change in storage modulus from a case where the loss modulus is higher than storage modulus to a storage modulus higher than loss modulus, that is a viscous behavior to a solid like nature happens, that is the crossover point. So these aspects were discussed in the cross linking lecture. And the final lecture was on conversion of polymers. This was on again uh, sustainability point of view. So what are the different conversion techniques, like your chemical recycling, it can be an incineration, or incineration with energy recovery, pyrolysis, chemolysis, fluid catalytic cracking, and hydrogen technologies like hydrocracking or gasification. So these can be used for conversion of polymeric materials. And what are the factors that affect the conversion of polymeric materials? For example, the monomer type itself decides whether depending on the functional groups and bonds available, they the ability to break that particular bond varies, and that affects the conversion. The temperature, catalyst used, pH, solvent used can affect the conversion of macromolecules. And what are the different solvents used, like water and alcohol can be used. And also there is a shift towards environmental friendly solvents like ionic liquids and supercritical fluids. And also how different kind of radiation can be used, like microwave, ultrasound, or light can be used, so for photo induced reactions. And what is the role of absorption and diffusion reaction? For example, as due to the macromolecular nature, the reaction can be confined to the surface, and then it can gradually, the reaction can proceed to the inner part of the polymeric system, or it can be a bulk reaction where the reaction happens everywhere in the sample. So these aspects were discussed. And the next was the chemolysis of PET. So how PET can be converted to its monomers using different processes was discussed. And then there was a discussion on combustion and incineration of polymeric materials, and how some advanced operations that are used for petroleum refining, like fluid catalytic cracking can be thought of, or hydrocracking can be thought of for polymeric breakdown. And then what are the carbon dioxide equivalent for materials like HDPE, LDPE or PET during combustion and incineration process. So these were all discussed in the lectures of week 10. Now let's get on to the uh, practice assignment questions. Question number 1. A continuous annular product is it produced by a compression molding, or is it produced by extrusion, or is it produced by blow molding operation, or is it produced by injection molding operation? So in which operation you can get a continuous annular product? So this is a GATE question which was asked in GATE 2014. The answer to this is extrusion. So extrusion is actually a continuous process where material can be continuously extruded from the equipment, whereas the compression molding, blow molding, and injection molding are all batch processes. Next, question number 2. Breathing operation is used for dash in dash processing technique. what is the purpose of a breathing operation and in which of the processing technique it used? So, your breathing operation is basically used for minimization of void generation or removal of gas or air entrapped. Because if air is entrapped in, for example, a particular polymer, then it can affect the behavior. The polymer is not continuous in that particular, part. Okay, so this can affect. So, in order to minimize the void or remove the gases or air entrapped, breathing operation is performed, and this is performed in a compression molding process where once the liquid polymer enters into the compression mold, and then the two platens are brought together, and then it is the platens are held for some time and then opened for some time and then uh, closed back, so that the entrapped air or moisture can be removed and thus helps in minimization of voids. Next, in polymers, due to their high viscosity, the mechanism of mixing is, what is the mechanism of mixing that that predominates in case of polymers because of its high viscosity? It is actually laminar mixing. So in polymers, the mixing happens as sheets of layer, one layer of polymer followed by the other. It cannot happen. Turbulence cannot happen in turbulent mixing. Cannot happen in case of polymers because of their very high viscosity. And this laminar mixing, it is based on your molecular and segmental diffusion. Okay, that is why mixing is very difficult in case of a polymer, because you do not have the turbulence uh, coming into picture. Next question, in a particular extrusion process, in order to get a rectangular extrusion profile, the die opening had the following shape. The rationale behind using a different or complex shaped die is, what is the rationale behind? So, in a particular extrusion process, the die had this particular complex shape in order to get a rectangular profile of the product. Why is it having a different shape compared to the uh, you know actual shape required out of the polymer? Why is it so? What is the reason behind using a complex shape? This is because this is due to the phenomena called dye swelling. So when macromolecules during an extrusion process, they are forced through a narrow opening, and this causes a forced segmental stretching and other operations at macromolecular level. However, once the extrudate comes out, uh, because of the inherent elastic nature, there is a recovery leading to conformation changing back to the original. So this causes kind of expansion and leading to a dye swelling. There are also other factors such as surface tension of the macromolecule and the surrounding air that leads to the fact that the shape of the extruded profile is different from that of the shape of the die. So in order to get a particular profile, the shape of the die cannot be the exact same. For example, a rectangular profile of particular dimension, you have to have a different profile. You have to understand the macromolecule molecular behavior and then design the opening such that you get the required profile because of the phenomenon of die swelling that is happening in extrusion. Next, the diameter of a die of an extruder producing extrudate of diameter 2.4 mm with a die swell ratio of 2 is dash mm. So, this is a GATE 2015 question. So, what is asked is that, so the extrudate from the extruder has a diameter of 2.4 mm and they have given the die swell ratio as 2. So they are asking what should be the diameter of the die. So obviously they given some diameter. That means the extruded profile is circular, correct? And the extrudate has a diameter of 2.4 mm, and we know that during extrusion there is a die swelling that is happening, and they've also given the die swell ratio is 2, and they have asked what should be the diameter of the extruder. So how do we proceed with this? The solution for this is die swell ratio is equal to extruded diameter to the diameter of the die. So we have die swell ratio as 2, extruded diameter as 2.4. So what is the diameter of the die? This is just mathematics. So you have 2 is equal to 2.4 by diameter of the die. So diameter of the die is extruded diameter divided by die swell ratio. So 2.4 divided by 2, that is 1.2 mm. So a 1.2 mm die can give a extrudate of 2.4 mm diameter. So that to that extent, the die swelling is happening. It is nearly doubling. Okay. So now let's proceed with the next question. Molecular dynamics deals with solving of dash balance or balances. So what are the balance equations that are solved for molecular dynamics? So this was discussed in flow simulation lecture. So it is actually the momentum balance equation that is being solved in molecular dynamics. Next question. Divergence of velocity is 0 for dash fluids. For which type of fluids is the divergence of velocity 0? So the answer is for incompressible fluids, the divergence of velocity is 0. Because in case of incompressible fluids, so if you see in rectangular coordinates, so you have the for incompressible fluids, obviously your uh, density is not a function of time and space. So density is constant. So if you write the mass balance equation, you have dou rho by dou t plus Vx into dou rho by dou x plus Vy into dou rho by dou y plus Vz into dou rho by dou z plus rho into dou Vx by dou x plus dou Vx by dou y plus dou Vz by dou z is equal to 0. So this mass balance equation, and we know that for incompressible fluid the density is constant. So the derivative of density with respect to time and space goes to 0. So you end up with the divergence of velocity, that is dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z is equal to 0. That is nothing but your divergence of velocity is 0. This is in terms of rectangular coordinates. So similarly, you can write for your spherical or uh, your other coordinate systems. Okay, spherical or cylindrical coordinate system, similar equation can be written, and the corresponding the divergence of velocity will be equal to 0. Next, identify the viscous dissipation term in the below equation. So you have the following equation. You have to identify what is the viscous dissipation term in this. So you have the equation as rho Cp into dou T by dou small t, where capital T is your temperature, small t is your time, plus rho into V dot gradient of temperature, V dot gradient of temperature is equal to kth, where k is your thermal conductivity into del square T plus sigma into your gradient of V. So this is the equation. So you have to find out which is the viscous dissipation term in this. So it is which of these terms? So it is the first term, it actually represents your internal energy accumulation. Okay. The second term where you have the gradient, this is V into velocity term, right? So this is a convective term, and here it is your conduction term, and the final term is your viscous dissipation term. And this viscous dissipation term becomes very important in case of polymers because viscous dissipation is very high. One is because polymers as such, they have very high viscosity, leading to viscous dissipation being very high. The other is again polymer operations like injection molding and all involves high shear rates. Okay, again this means that the gradient of velocity is going to be this grad V is going to be very high. So again further, this means that the viscous dissipation is going to be very high. So viscous dissipation is a dominant mechanism. In fact in polymers you can say that the convection term is not going to really play a very critical role, because you do not have convection. It is going to be just laminar flow. Okay. And similarly, conduction term, the conductivity of polymers is also not very high. So the conduction term of the heat balance equation is also not going to play a very critical role, whereas the viscous dissipation plays a very critical role in case of polymers. Next question. Recycling polymeric materials in the same application is open loop recycling. Is it true or false? So it is actually false. So recycling polymeric materials, for example, a mold overflow can be recycled in the same, for example, in car manufacturing or somewhere, there can be mold overflow. This mold overflow can be taken and can be reused. So this is a closed. So within the same application, it can be reused. So it is not a recycled. So it is not a open loop recycling, but it is a closed loop recycling process. And this is also called as a primary recycling process. Next question. Viscosity of LDPE increases from 2000 to 13,000 Pascal seconds after 100 cycles of recycling. What is the reason behind this? What causes this viscosity increase of LDPE from 2000 to 13,000 Pascal seconds after 100 cycles of recycling? So the reason behind this is that cross-linking reaction starts taking place in LDPE, leading to increase in molar mass, because once you cross-link, the molar mass is going to increase, and molar mass is increasing, obviously your viscosity increases. Okay. So that is the reason for your viscosity to increase after 100 recycling operation in case of LDPE, and this is an undesirable phenomena, which is again a drawback of mechanical recycling process. Okay. Now let's go on to the next question. In twin screw extruder, dash screws helps in high pumping efficiencies, while dash screws helps in high dispersion efficiency. Which type of screw operation helps in high pumping efficiency, and which type of screw operation helps in high dispersion efficiency in case of twin screw extruder? So it is actually a co-rotating operation. It helps in high pumping efficiency because both the screws rotate in the same direction, and this leads to double transport action of two screws. So you can pump the polymer melt easily. Whereas in case of in order to have a high dispersion efficiency, you can have a counter rotating screws. So in counter rotating screws, since both screws are rotating in opposite directions, this causes a dispersion due to calendering action between the two screws. Okay. Now let's Let's move on to next question. Resin transfer molding is used for dash parts with dash kinetics. So, what is the size of the parts that can be molded using resin transfer molding, and what is the type of kinetics that happens in case of resin transfer molding? Also, what kind of kinetics happens? What kind of kinetics is applicable? Can be suitable for resin transfer molding. So the answer is, so resin transfer molding, it can be used for large composite parts. Okay, like for your aerospace and all, you can have large composite parts that can be manufactured. But the mold shape, and you can have only simple mold shape, and we cannot have very complex mold shape in resin transfer molding. And also, the kinetics should be slower kinetics. So that is your cross-linking and polymerization, and sorry, your cross-linking operation especially, and curing operation should be very slow, because the mold will be very big, because the composite part that is to be made is very large. So the entire polymer, it has to flow through the entire mold, and then it has to take the shape of the mold. So if it is going to cross link at very fast kinetics, then when you just start transferring it to the mold, the cross linking action takes place and the material gets cured. So you will not end up with large parts, but you will end up with small portions, or non-uniform property you will end up with. So in order to have a uniform property, a slower kinetics, the systems that can undergo slower cross-linking operations or slower kinetics of operations, can be handled using resin transfer molding, and this further helps in making large composite parts. So this is how it happens. So your preform of your reinforcement is placed on the mold, and then the mold is closed, and then your resin is passed through the entire mold. So if the resin is going to cross link, if it is going to be very fast in cross linking, when you just start transferring it into the mold itself, it will start cross linking, and that is not desirable. So it has to have a very slow kinetics, so that the entire resin is passed through the entire mold, and then the cross linking process happens, and then the part is removed, the big composite parts are removed. Next question. Identify the mechanical and chemical upcycling process from the below. So there are certain processes given below. We have to identify which of the process corresponds to mechanical upcycling and which of the process corresponds to chemical upcycling. Post polymerization modification to improve processability. Next is use of as a particulate reinforcement. Next, functionalization to improve compatibility of recycled blends. Next, chemicals with high value. And final is sorption and removal of volatile organic compounds. So we have to identify which kind of upcycling does each of these belong to. The answer for this is post polymerization modification to improve processability. It is a chemical upcycling. Okay. So after polymerization, you can improve the processability, means you have a chemical upcycling involved. Whereas use as a particulate reinforcement, it is a mechanical upcycling process. Okay. And the next, functionalization to improve the compatibility of recycled blend. Obviously, you are doing some chemical operation, that means functionalization you are doing. That means it is a chemical upcycling. Okay. Next, chemicals with the high value. Obviously, you are doing a chemical upcycling again here. And then Sorption and removal of volatile organic compounds. It is a mechanical recycling operation. Okay. So these are some of the chemical and mechanical recycling operations that are done. Next question. Stretching is a processing step in blow molding operation. Is it true or false? Is stretching a step in blow molding operation, or is it not a step in blow molding operation? We have to identify whether the statement given is true or false. It is actually true. So stretching is a processing step in blow molding operation. So these are the steps in blow molding operation where you have, initially, your partisan or preform placed in the mold, and then your mold is closed. And once the mold is closed, first, in fact, first the mold heating happens, and then your mold is closed, and in the closed mold your partisan is inserted. Once the partisan is inserted, now because of the heat applied, now it would have gained some amount of flexibility. So, and then it is stretched, and following stretching, blowing operation takes place. So this causes the expansion to the required shape of the mold, and once it is taken up the required shape, cooling of the mold takes place, and then the mold opens and your final product comes out. So these are the steps involved in a blow molding operation. Next, in a pipeline over long distance with a constant area with constant flow rate, that is a steady flow, in other words, polymeric material can be considered as dash, while in an extrusion or injection molding process through complex geometries with unsteady flow, polymeric material should be considered as dash. So this is based on the polymeric flow. So how do you, how can you, consider the polymeric material? So for the first case, where for example a polymeric melt flows through a long distance through a pipeline that is having a constant area and the flow rate is also maintained constant, that means this is a steady state flow. Okay, so because of the steady state flow and it is over long distances, you can consider, you can eliminate the elastic response. Okay, because the strain rate, it is maintained same because of the steady flow, and the geometry is also constant area geometry. So because of this, you can consider the polymeric material as a viscous fluid, and the calculations can be made. Okay, while in an extrusion process, or in an on a stretching process or in an extensional flow process, so here the shear rates are high and the shear flow is unsteady state flow, and your polymeric material, it flows through complex geometries. You can we have seen in the lectures that in injection molding and all, you can make complex geometries and complex molds and all can be made, and complex parts can be made. So so here, obviously your elastic nature, for example in extrusion you saw the the die swell phenomena, that is because of the elastic nature, correct? So it is trying to come back after it is forced through and stretched through the extruder, which is of a smaller dimension. When once it comes out and meets the natural environment, or the open environment outside the extruder, because of the elastic nature, it's the actual shape and the die shape are not same. This is because of the elastic nature of the material. So obviously you should consider the material, the polymeric material, as a viscoelastic material, and then the corresponding calculations should be made. Okay, next question. The extent of reaction for cross-linking in step growth polymerization is directly proportional to the average functionality. Is it true or false? Is the extent of cross-linking reaction in in step growth polymerization directly proportional to average functionality? So is it true or false? So the answer is false. In case of step growth polymerization, your extent of reaction is inversely proportional to your functionality. So if you have higher and higher functionality, your the extent of cross-linking reaction required to cross-link the polymer is lesser. For example, if your functionality is 2, so 2 by 2, for example, consider n tends to infinity. So in order to achieve 3D network, so for example, when you have your FM is your average functionality. For example, if you consider functionality as 2, then your extent of cross-linking reaction is equal to 1, right? In order to achieve a 3D network. Whereas when your functionality is 3, assuming that n tends to infinity, when your functionality is 3, you have your extent of cross-linking reaction as 2 by 3, which is only nearly 6% of cross-linking reaction, extent of cross-linking can form a 3D network. Okay, so it is inversely proportional to the average functionality. Next question. According to Winter-Chambon criteria, dash is independent of dash at the gel time. Where is your Winter-Chambon criteria used? And what parameter is independent of what parameter in that, according to the Winter-Chambon criteria? So according to Winter-Chambon criteria, your tan delta is nothing but your ratio of your loss modulus G double prime to your storage modulus G prime. Okay, that is your viscous nature to your elastic nature. Okay, that becomes independent of frequency. Okay, so it becomes independent of frequency. So if you plot tan delta versus time for different frequencies, so at gel time, according to the Winter-Chambon criteria, it becomes independent of frequency. The tan delta becomes independent of frequency because your G prime is a function of frequency and your G double prime, your loss modulus, is again a function of frequency, and both are similar functions of frequency. And what happens is that when you take the ratio of G double prime to G prime, the concept of frequency will fall out and it becomes independent of frequency at gel time. And you can find out what is a gel time when you plot your tan delta versus time. So this point is your gel time. So yeah, all the curves, it comes and it's at a single point. So this is your gel time, where your it gets converted to a gel, or your the polymer becomes from a more viscous like polymer to a solid like polymer. Okay, next. In chemolysis conversion of polyethylene terephthalate, use of methanol leads to production of ethylene glycol and dash, while hydrolysis of PET leads to production of ethylene glycol and dash. So chemolysis means using chemicals, okay, to break down polyethylene terephthalate. Chemolysis means using chemicals. Lysis means breakage. Chemo means using some chemicals. Okay. Here, there's a discussion of two different processes. One is using methanol and the other one is hydrolysis. Hydrolysis is nothing but use of water. So when we use ethanol, what is the monomer we end up with when we want to break polyethylene terephthalate? And when we use water for breaking polyethylene terephthalate, what is the monomers we end up with? So when we use methanol for breaking polyethylene terephthalate, we get monomers ethylene glycol and dimethyl terephthalate. While when we use water, we end up with ethylene glycol and terephthalic acid. We know that polyethylene terephthalate is nothing but your ethylene, it is formed due to reaction between ethylene glycol and terephthalic acid. So when we use methanol, so this is what is the reaction. So this is the structure of your polyethylene terephthalate. So you will get, when we use methanol, you will end up with, your COO getting connected to a CH3. Okay, so you will end up with a dimethyl terephthalate. Okay, ester. Okay, and then ethylene glycol. Whereas when you use water, you will end up with the acid, that is your terephthalic acid, and this, in fact, the reaction shows a alkaline hydrolysis. So because the hydrolysis can happen in the presence of acid or in presence of uh, alkaline medium as well, and you end up with the terephthalic acid, your acid compound. Okay, so we can identify that you end up with different monomers if you use different chemicals for breaking a polymer. Okay, now the next question is, a rubber compound is made by mixing functional additive with rubber using what? So which of the equipment can be used for mixing a functional additive with rubber to make a rubber compound? Can we use a two-roll mill, or can we use compression molding machine, or can we use three-roll calender, or can we use a thermoreforming machine in order to mix an additive with rubber to form a rubber compound? So this is again a gate question. So the answer is, you use a two-roll mill in order to mix a additive with a rubber to form a rubber compound. Whereas compression molding or three-roll calender or thermoforming machines are all shaping operation machines. Whereas a two-roll mill is a mixing operation machine. Okay, this is how the two-roll mill looks like. It will have two rolls, and the material is passed through the two rolls through which the mixing happens. Okay. Next question. Arrange the processing operation of polymers in the increasing order of their cycle time. So we have certain polymer processing operation. We have to identify what is the cycle time for each of these operation and arrange according to the increasing order of the cycle time. For example, which based on which requires minimum time and which process requires maximum time. Okay, rotational molding, thermoforming, injection molding, compression molding, and blow molding. Which operation requires very low time and which operation requires high time among the given set of polymeric operation. So the answer is injection molding. This requires the least time. It in fact requires 2 to 10 seconds, to perform this operation to get an output. Okay. Whereas your blow molding operation, it requires 10 to 15 seconds. And then thermoforming requires nearly 1 minute. Compression molding requires 2 to 6 minutes. Whereas your rotational molding requires, this is used for making your, water storage tanks and all. You have to form, thick, the thickness of the tanks, should be very good so that it can hold, a large volume of water and all. So it requires 30 minutes. So you can see that, how low is the, how much low is the cycle time for a polymeric operation, and that is why we end up with using polymers across different applications. Okay, so that's it with the session. So that is it with the session. Thank you all. Thank you all. Have a nice weekend.